Hello and welcome to the LUniverse virtual planetarium from Lancaster University. The following is a recording of one of our free live public shows that we ran during early 2021. I hope you enjoy.
Now, unfortunately, just like last month, now it's not a great time to observe planets, as many of them are out at the same time as the sun. And also the night is quite smaller than it is during the winter time. However, something exciting is happening at Jupiter, which, if you have a telescope, might be exciting to see. On the 5th of June at 2 a.m., Jupiter will be between east and southeast, and Jupiter's moon Io will pass in front of Jupiter, casting a shadow on the planet. At the same time, Ganymede will cast its own shadow on the planet. So you will have a picture of Jupiter with one of the moons in front of it and the shadow of two moons on the surface of it. And of course, a few days later, we will have a pretty rare occurrence, rare-ish. We will have a partial solar eclipse visible from here in the UK. Now, a solar eclipse is basically when you have the moon passing in front of the sun and covering the sun. We know that the sun is really huge, but also it's really, really, really far away. So the size of the moon and the sun, from our perspective, is comparable. Based on the fact that the orbit of the moon is not exactly circular, there are some times that the moon is closer to us, making the moon look bigger to us, and sometimes it's farther away, making the moons look smaller. Therefore, we have three types of solar eclipses. We have a partial eclipse, a total eclipse, and an annular eclipse. A partial eclipse is when the geometry is a bit off and the moon only covers part of the sun. The total eclipse is when the moon covers the entire of the sun, and an annular eclipse is when the moon does cover the sun, but it's not as big as the sun itself. And the result of that is a really nice halo around the moon. Total eclipses last typically a few minutes, in opposed to total lunar eclipses that could last many hours. The maximum for this eclipse that will take place is going to be on the 10th of June at 11:14 a.m. This eclipse is going to be seen as annular over the Northeast Canada, Greenland, the Arctic Ocean, and the Russian Far East. But as the UK is quite far from the path of totality, it will be visible as a partial eclipse here. And I need to say that you absolutely need solar glasses or a proper solar telescope in order to watch the eclipse. Looking directly at the sun can be quite dangerous, so please be safe when you're doing that. Later, a couple of days later, or some days later, on the 21st of June, we will have the summer solstice. And on the 13th of July now, we will have a conjunction of Venus and Mars. The two planets are going to be so close that you will not be able to separate them with just your eyes. This event is taking place at west-northwest, but unfortunately, there is a pretty good chance that the sun blocks it out, as it is quite close to the planets. If you want to give it a go, it's going to be visible just after sunset around 10 p.m. And later during the summer, we have, from a lot of people are calling it the star of the summer, and I can totally understand why. We're gonna have the Perseids meteor shower that's gonna peak between the night between the 12th and the 13th of August. we could potentially have up to 60 meteors per hour. And the fact that we're going to have a waxing crescent moon means that the sky should be also dark, and fingers crossed, without too many clouds. You can watch the meteor shower at the northeast above Perseus, and the Perseus is a meteor shower that it's going to be good from sunset onwards until the sunrise of the next day. And later in the year, on the 23rd of October, we are excited about something amazing. Well, it's not an observation, but it's something that's worth getting excited about. On the 31st of October, we will hopefully have the launch of the James Webb Space Telescope that is considered to be Hubble's replacement. So all of us here and all the scientists around the world are looking forward to receive all the data from this new telescope. Now I am giving the stage to Julie to tell us all the exciting things about galaxies.
Thanks, George. It's great to be here and it's great to speak to you all. Hopefully my slides should be visible, I'm not sure. Yep, brilliant. So I'm going to talk about galaxies, and I'm going to start by talking about the sorts of galaxies that we see in what we call the local universe. So that's nearby to the Earth. And then what I'm going to end up going through is how we think the universe has ended up this way. So what caused galaxies to evolve into these distinct shapes and patterns and categories that we see locally. So the images here are three different types of local galaxies. So we've got the big elliptical galaxy on the left. So that's the one that's kind of orange and really just a bit of a blob or a smudge. There's not much structure to it. And that's actually one of the most massive galaxies in the local universe. So elliptical galaxies tend to be the biggest types of galaxies. So even though it doesn't show it on the screen, that one is bigger than the other two. And then on the top right, we've got what probably many people think about when they think of a galaxy, which is what's known as a spiral galaxy. That one happens to be the nearest big galaxy to our Milky Way. That's M31 or Andromeda. And then on the bottom right, we've got what's called an irregular galaxy. And it was very hard for me to find a picture of an irregular galaxy because they're all different. So there's loads and loads of images of different irregular galaxies, but there's not one common theme between them. And so what we need to do is think about how to classify galaxies. And that was first done back in the early 1900s by Hubble. And Hubble classified galaxies according to what's called this tuning fork diagram. And so on the left, we've got the elliptical galaxies, and there's different types of ellipticals. They come with different numbers, and that's just how flattened they are. So whether they're properly round or whether they're a bit flat. And then on the right, we've got two strings of what's called spiral galaxies. So these are the ones that have those winding arms around them. They tend to be bluer. So you can see the stars around the edges of those spiral galaxies tend to be blue, whereas the ellipticals tend to be red. And that's because the stars are different ages. So younger stars tend to be blue and older stars tend to be red. And then in the middle there, we've got what's called a lenticular galaxy. And that's one that's kind of straddling between the ellipticals and the spirals. And then the different types of spirals, we've got at the top unbarred spirals and at the bottom barred spirals, where the bar is the bit across the middle. So when you look at those, the ones at the bottom, you can see kind of a line through the middle. And that's what makes these barred galaxies or barred spirals. What you're not seeing on here is any of the irregular galaxies. So they are normally shown kind of separately from this sequence. Now, Hubble put this together and he thought this was a sequence of evolution from left to right, so from ellipticals to spirals. But what we know now is that that's just not true. And it's more likely that we're evolving from right to left. So spirals may eventually become ellipticals, but it's not quite that straightforward. There's a little bit of weirdness happening in the distant universe, and there might be interactions between different galaxies that cause their form to change and things like that. And so understanding how we get these neat classification of galaxies is a really big question within astronomy. So what makes one galaxy a spiral and another galaxy an elliptical? And then you know, it's not even true that there's not that many galaxies. So most of these pictures, if you look closely, you can see other things in the backgrounds. And those are often other galaxies in the background. So we've taken a picture of this main one that's in the foreground, and that's filling up the field of view. But in the background, there might be some galaxies as well. So if we point a telescope at a patch of sky that looks blank to our eye, you'll see something like this. So this is the Hubble Extreme Deep Field. And basically everything in here is an entire galaxy. So some of the ones that are a bit closer to us, you can see the structure. So you can pull out some elliptical galaxies, some spiral type galaxies. Well, there's also 1 or 2 stars in here, but they're very, very rare. And then you can see others that are kind of smudge-like, and others still that just look a bit like dots, and we can't really see what's going on. And so by doing this, by just taking a picture of what seems to be a blank patch of sky, we can take a census of how many galaxies there are out there. But what sort of scales are we talking about here? Because these galaxies, you know, they look very different from the ones I showed you before, and that's really just because they're further away. So exactly how far away are we thinking? Well, if we think about how far the Earth is from the sun, which I know, you know, that's not normal everyday thinking, how far away is the sun? But that's 93 million miles, which is about 12,000 times the width of the Earth. So if you were to drill a hole through the center of the Earth and then put that 12,000 times together, you'd get to about the sun. So that's already pretty far. It would take a long time to travel. You'd probably get hungry on the journey. But then we've got the distance between the sun and the next nearest star, and that's 25 million miles, thereabouts, which is 270,000 times the Earth to the sun distance. So we've already jumped a huge amount just to get to the next nearest star. There's this huge step in distance. If we want to think about galaxies then, and we think about how far is the Milky Way, which is our galaxy, or the sun, to the next nearest big galaxy, or to Andromeda, that's 15 trillion miles, or about 600,000 times the distance between the sun and the nearest star. So these are really massive distances, and it's really hard to kind of get your head around them sometimes. It's really hard to fathom them. And that's just the nearest galaxy. So that's one of the ones that we can take really, really gorgeous pictures of. The ones that I was showing you before are even further away than that by quite a lot. So instead of thinking about miles or relative to things on the Earth, we astronomers often use light years and light minutes. And I want to emphasize here that light years is a measure of distance. Even though it's got year in it, it's not a measure of time, it's a measure of distance. So a light year is the amount of distance that light can travel in 1 year. So if we think about this from the Earth to the sun, it takes light about 8.3 minutes to travel that. So we could call that distance 8.3 light minutes. And this is because light doesn't travel at infinitely fast speeds. It feels infinitely fast to us on Earth because we have no distances that are big enough for us to see a lag in how quickly the light travels. But if you look at the sun, we see things about 8.3 minutes after they happened on the surface of the sun. The nearest star to the sun is 4.4 light years away. So that means it's taken that light 4.4 years to get to us. If we're looking at Andromeda, which is our nearest big galaxy, we're talking about 2.5 million light years. So it's taken 2.5 million years for the light to get from that galaxy to us. So that means that something could have happened in that time, and we wouldn't know about it yet because the signal wouldn't have reached us yet. So that we need time for the signal to get to us. And this is kind of cool because it means that we can effectively look back in time. So being an astronomer is a bit like being a time traveler because we're seeing things as they were in the past. And if we think about this on the scale of the universe, we're talking about really massive time. So the universe started with a Big Bang, which is depicted here on the top right. And after the Big Bang, you know, the universe was very, very hot. There wasn't much going on. And eventually the first stars started to form. And so if we were to try and observe the most distant thing that we could see, it would probably be those first stars, you know, if we had really powerful telescopes and things. So if we could see those first stars, we're looking back in time almost 13.7 billion years because it's taken the light that long to reach us. So by effectively looking at things that are really far away, we're looking at things that are really far back in time. So by looking at further and further distant galaxies, we're looking at them earlier and earlier in their evolution. And it's that way that we can try and study the evolution of galaxies, because we can see snapshots of galaxies as they've evolved. So if we look at a galaxy that's, say, 10 billion light years away, we see it as it was 10 billion years ago. Then we could look at a different galaxy that was, say, 8 billion light years away. So we're seeing that one as it was 8 billion years ago, and we could try and join the dots between those two and figure out what is causing that galaxy to evolve, and see how galaxies are evolving in that way. And this is something like, if you came down to Earth and you didn't know what was happening, you didn't have time to wait for a human lifetime, you might walk down a high street and see some babies, some toddlers, some young children, some teenagers, and some adults. And from that, you might be able to infer how humans change through their lifetime. And that's really what we're trying to do with galaxies. And so we can try and visualize this in a bit more of an intuitive way. So what I'm going to show you next is a video. And in that video, we're going to start near the Earth and we're going to fly away from the Earth. So we're just swinging around from Orion to find a patch of sky that is really, really dark. So we're finding the darkest patch of sky we can, and we're going to travel away from the Earth. It's going to get pretty fast, I warn you. We'll travel away from the Earth, and we're going to look at all the galaxies around us. So the galaxies that we see first, they're the galaxies that are nearest to the Earth. And the galaxies that we see later, they're the ones that are furthest from the Earth. So as we start to get into where the galaxies are, you can see that there are some spiral galaxies, there are some elliptical galaxies. There's quite a variety of colors in these galaxies, and you could probably classify them according to that Hubble tuning fork diagram that I showed fairly easily. Now, all of these galaxies, these are real data. So this is proper images of real galaxies, and they're at their correct position in the universe. So we've drawn them where they really are, and we've put them at the distance away from us that they really are. So as we're getting further and further away from the Earth now, you can start to see that these galaxies are getting much smaller. There's becoming much less variety in their shapes. So the structures are different. It's less easy to classify them, obviously, into spirals or ellipticals. And so what we've done is we've started to see that evolution just by traveling away from the Earth. We can see that visually. But then what astronomers, of course, want to do is study this in a scientific way. So we measure these structures, we measure the light that's coming from these galaxies. But this isn't even the whole picture. There's another part to this equation. And the other part to this equation is that environment matters as well. So that fly through that I've just shown you, that is based upon picking a random patch of blank sky. So we've not selected that for any reason. If instead you go to a patch of sky that's got lots and lots of galaxies close together, you see something more like this. And this is what's called a galaxy cluster, or a cluster of galaxies. And this galaxy cluster has a lot of these elliptical galaxies. So you can see most of the galaxies here, they don't have spiral structure. They're more kind of blobby and smooth in their structure. They're mostly very, very red. There are a couple of stars in this image near the top that you can see. And there's a couple of foreground or background spirals as well. But for the majority of the objects that are in this galaxy cluster, they're elliptical galaxies. So that suggests to us that there's something about the environment, there's something about the area in which a galaxy lives that causes it to become an elliptical galaxy, or there's something about the types of galaxies that form within a cluster that means that they were always going to become elliptical galaxies. So we've not just got the evolution of galaxies, random within the universe, but we've also got some kind of environmental impact happening as well. And if we're going to understand how galaxies evolve, we need to make sure that we're accounting for all these different things in our theories. The other thing we have is that I've cheated a little bit, and so far I've only shown you optical images. So that means that if you had huge space eyes, if you could go outside and make your eyes into giant telescopes and kind of zoom in visually, you would be able to see the sorts of images that I've shown you. Now, of course, none of us have giant space eyes, but we can dream. But there is a whole rest of what's known as the electromagnetic spectrum that covers more than just the bit that we can see. So for example, there's infrared light. So if we looked at a picture of a dog with our eyes, we'd see something like the one on the left. If we were to look at that dog in the infrared, we'd see something more like the one on the right. And this infrared light is telling us about the heat that's coming from that dog. So it's got very hot eyes and a very cold nose. You can see the chain around its neck because the chain is colder than the rest of it. So this infrared light is giving us extra information that the optical isn't. And the same is true for galaxies. If we look at different wavelengths of light, different types of light, we gain extra information that we wouldn't otherwise be able to see. Now, there's a nifty little experiment that we can do to prove to you that infrared light really exists. And this is an experiment that you can try at home later. So if you take a normal remote control, so I've got here my TV remote control. If you were to just look down the end of that and press the button, you would see something like the image on the right. So there would be nothing. So most remote controls, they don't have a light or anything that comes out that we can see. And that's basically what you see here. So there's nothing coming out of the end of that remote control now. That's just where the signal will come. If I now press a button on here, you should see it starts to flicker. And that's the signal that's coming out, and that's the infrared signal. So just do that again. So it's flickering right out the end there. And that's the infrared signal that my remote control would be sending to my television. And that's how my TV knows what the remote control is saying. Now, the reason that you can see it when I point it at the camera is because my my webcam is sensitive to infrared light. And in fact, it turns out that most CCD cameras, which means most digital cameras, they're sensitive to that light. So you could look through your own webcam or a phone or whatever else and try this with your own remote control. And for most of those, you'll be able to see the signal that's coming from your remote control when you point it at the camera. There's a minor caveat there. I don't think this works with some of the latest iPhones, and I don't know about all the other brands, but you can try it with different devices around your home and see which ones have a filter on that blocks that light and see which ones don't. And you'll be able to see the infrared light with some of those cameras. So what does this mean for galaxies then? So if we look at the whirlpool galaxy, this is M51, the middle panel here is what you would see in the optical. So giant space eyes, you'd see the middle panel. But then we've got these other types of light. So we've got to the right, light that is more energetic, which has shorter wavelengths. So that's the ultraviolet and the X-ray. And they trace things that are very, very hot. So you can see that compared to the optical image, the ultraviolet one is tracking the areas that seem quite blue on the optical image. And that's where there's fairly young stars. So they're very, very hot stars because they're quite young and energetic. And then the X-ray, you can see even fewer things. The middle is very lit up in the X-ray, and there's a region to the top as well, which is actually a second galaxy in this image that's lit up in the X-ray. And that's where there's a black hole at the center of this galaxy, which is very energetic in the X-ray. And then there's a couple of other, or quite a few other dots and spots around here in the X-ray. And those are what's called X-ray binary stars, which are also extremely energetic, and that's why they're lit up in the X-ray. If we look to the other side of the optical image, so if we look at the longer wavelength, and to the left of the optical image, we've got the radio and we've got the infrared. So these are longer wavelength, which traces lower energy emission, so cooler emission. And so you can see, for example, in the infrared image, a lot of what's lit up there was actually very, very dark in the optical image. So if you only had the optical image, you might look at some of those brown patches and think, oh, there's nothing there in the galaxy in those regions. But in the infrared image, you can see something. You can see these same areas are really brightly lit up. And that's because the infrared is tracing regions that are covered in dust or engulfed in dust. Now, when astronomers say dust, they mean really, really fine particles, and they're just kind of floating throughout those regions of that galaxy. So it would be something like smoke that obscures your vision, but if you put an infrared camera on it, you can see the fire behind the smoke. And then in the radio, which is even longer wavelengths, even lower energies, we can see the bars of this, the spiral parts of these spiral arms very brightly there. And that's because, again, the types of stars that emit in the radio happen to be where the main section of those spiral arms are. So really what we can tell from this is that if you want to study the universe, you can't just do it in the optical. You really need to study a whole range of data and look at all different multi-wavelength data. Now, the stuff that I focus on in my research is the infrared, because that tells us a lot about what new stars are forming and where the energetics are, where there's a lot of ongoing star formation. And it turns out that if we look at the infrared for different types of galaxies, some of them are wildly different to others. So here we've got two different galaxies, and on the right of each pair is an infrared image, and on the left of each pair is an optical image. So if you just had your giant space eyes, you'd see the left-hand image of each of these. And then if you look at this at the infrared, you get a wildly different picture. So the one at the top, that's Andromeda again. And you can see the dust lanes in Andromeda really lit up in that infrared image. So that's telling us again that the dark patches, they're not actually because there's nothing there, it's because there's stuff there, but it's dusty, and that dust is obscuring or hiding what's behind. The galaxy at the bottom is the Cigar Galaxy. And this one looks wildly different in the infrared. You can see all these red filaments coming up from the top and the bottom of the central part of this galaxy, and that's because there's a lot going on in this galaxy. We think that in this particular case there's material being blown out of the galaxy that's going above and below it due to the amount of star formation that's happening in there, and the infrared is really telling us about that. So if we want to study the universe, we need to look at lots of different wavelengths, and for some galaxies you might look at the optical image and get most of what was going on. But for some galaxies, if you just look at the optical image, you're going to miss most of what's going on. And it turns out that if you add up all of the light over the history of the universe, about half of it has been absorbed by dust and re-emitted in the infrared. So that means that about half of the light is just gone from the optical. You'll never be able to see it again in the optical. So if we want to study that, if we want to study what's happening in that half of the universe, we need to use the infrared. So we need to use these longer wavelengths observations. So, you know, half of the universe, that's a pretty big chunk to miss. So there's an idea of how important it is to do this. So one of the things that we can do is take an infrared telescope, such as the Herschel Space Observatory, and point it at a blank patch of sky. And that's what's shown in this image. So the Herschel Space Observatory is an infrared telescope, and it scanned a lot of blank patches of sky. So the background here is the main image, and then I've just zoomed in on a region in the little corner part. And I've done that zoom in to show you really what's going on there, because you can't see a lot of it from that background image. The background image shows that there's patterns and there's structure, and there's maybe variations in color. And it shows you that some regions, they've got more things clumped together than others. But you would be hard pressed to identify that as being individual galaxies. Whereas if we look at the zoom in part, you can see there that these are actually individual dots within this image. And each and every one of those dots is a galaxy. So every single part of this image is just covered in galaxies. In fact, there's so many galaxies here that there's no true black background. So even the bits that look pretty black here, they're not. There's galaxies underneath. It's basically galaxies all the way down. And these galaxies are really interesting because they're extremely bright in the infrared, and that tells us that they're forming an awful lot of stars. But there seems to be, you know, they're everywhere, and there's not really anything that picks them out from a normal galaxy. So if you look at an image of these in the optical, you wouldn't necessarily be able to pick out which ones these are and which ones aren't. But what we can do is do a fly through of the exact same patch of sky that I showed you earlier. So the one where we traveled away from the Earth earlier. We're going to take that journey again, but this time we've covered up, we've added in all the galaxies that have this bright infrared emission. So all these galaxies that you would see in that image are now highlighted in red. So that's why this first stretch is shown in red. So that's the infrared emission from our own Milky Way there. And as we travel away from the Earth, you can start to see there's some red galaxies here. So all of those red blobs, those are these really bright infrared galaxies. So you can see they're kind of scattered around. And it turns out that most of them are fairly far from us. So the majority are about 10 billion years away from the Earth, 10 billion light years away. So that means that they're fairly early in the history of the universe. So there's probably something about this population of galaxies that is important in the evolution of galaxies, because why else would there be so many of them in the early universe, or in the Middle Ages of the universe? Let's say it's not right back at the beginning near the Big Bang. So they must be something important. And what we can do is calculate things like how far away they are, how massive they are, how many new stars are forming, how compact they are compared to other galaxies. And so here's some data. So this is real data now. The red regions here are the dust emissions. So the red is the infrared, and the blue and the green is the existing stars in these galaxies. So all of that energy that's in the infrared tends to be fairly compact compared to the existing stars. So what we've got here is a massive burst of new stars forming in a fairly small region within these galaxies. So these galaxies in that central red bit are forming new stars about 1,000 times faster than our own Milky Way is forming new stars. So 1,000 times quicker star formation, and it's in that central region for the most part. And then we've got this other structures around them, and you can see from the green and the red that these are not the green and the blue, these are not obviously spiral galaxies or elliptical galaxies, or really anything that we would recognize from the tuning fork diagram as being classifiable in our local universe. So we need to try and understand how a galaxy is evolving, and when you see things like this is telling us about what's happening in the early universe. So we can say, oh, about 10 billion years ago there was this population of galaxies that are forming new stars incredibly quickly. These galaxies are pretty massive, and they have a lot of gas in them, and gas is the fuel for new stars as well. So one hypothesis for these is that they might turn into those elliptical galaxies that we see tending to be in galaxy clusters today. So maybe these galaxies are the early phases of what will become those biased environments that have a lot of elliptical galaxies close together. But okay, let's reset. Let's think about galaxy evolution as a whole. So that's one population that is giving us a clue as to what's happening. But can we study, as I mentioned before, steps across the history of the universe and try and figure out what's going on? So we have the Big Bang, and after the Big Bang, it's very, very hot. So the universe first has to cool down a bit, and it does that as it's expanding, it cools naturally. And then the first generation of stars and galaxies are formed. So this is a galaxy called CR7 that is quite close to the Big Bang. Now the main image here, that's an artist's impression of what this would look like if we could get pretty close to it. The little panel at the bottom right, that's what the data look like, or some of the data. And so it's from those data that the artist's impression has been made. So this is an example of one of the first galaxies. So what you can see is that this galaxy is very blue. So there's a lot of young stars in it. That makes sense. Those stars are quite hot, and that's because the first generation of stars would have to be hot because they can only be made of hydrogen and helium, because that's all that was formed in the Big Bang. And we've got these patchy regions of stars. So the stars aren't evenly distributed. We've also got some dust and clumpiness going on here. So this galaxy has not got any kind of regular shape. It's a bit of a hodgepodge of things pulled together. And that's just because it's so early in the universe, there hasn't been time for anything to evolve into a smooth shape or a spiral shape. But as the universe evolves, and as this galaxy itself evolves, so as those stars age, they'll explode, there'll be a new generation of stars formed. As all of that's going on, this galaxy will start to become a lot more coherent in its structure. But then something might happen. So for example, you might have a merger with another galaxy. And we know that there's a lot more mergers in the distant universe compared to locally. So if you've got two galaxies that happen to come close to each other or go past each other, they could hit each other. Even if they don't hit directly, the gravity between the two can impact both of them, and it can cause them to spiral together, or it can cause their stars to be stretched around and scattered about. And that can also affect the gas in the galaxy. And because the gas is the fuel for making new stars, that can change what's going on with the star formation. So this is an example of a galaxy sort of in the Middle Ages of the universe. This is a galaxy called Cosmos Aztec 1. And again, we've got the artist's impression as the big image, and then the data as the smaller image in the bottom corner. And this galaxy is thought to be one of these really bright infrared galaxies that's making huge numbers of new stars. And you can see from that artist's impression, there's kind of three main points to this. And we think that's because this is a galaxy that's got three components that are all interacting at the same time. And so this is a really big, energetic period in this galaxy's history. And so it's probably causing a lot of new stars to form. So we've got straight after the Big Bang, the first galaxies forming with very hot stars, quite clumpy structure, not smooth. And then as time goes on, the universe kind of calms down, those galaxies calm down. But at some point in their history, they might interact with another galaxy, and that can cause a kind of explosion in the star formation rate and something like this to happen. And then eventually the gas will run out in that galaxy, and it will then calm and it will stop forming new stars. It might be that the gas runs out because enough, so many stars have formed that there's none left. It might be that the stars or the black hole within that galaxy actually push some of the gas out, and then they can't form new stars again. But eventually this will calm, and as the universe evolves, as time goes by, this will start to spiral together again. And you'll end up with this picture of the local universe where you've got spiral galaxies and elliptical galaxies that are easily classifiable. Galaxies are one or the other. There's a few irregulars, but they're much rarer. And the ellipticals tend to hang out together in these galaxy clusters. So that's how we think it's happening. That's not all just come from data. So we can also use simulations to study these galaxies. And so I'm going to show you a video from a galaxy evolution simulation that starts near the Big Bang. And we're going to look at the different components of the galaxy in turn. I'll talk you through which ones they are. And we're going to see this simulation evolve with time. So what they've done is started off with conditions similar to what we think they were right after the Big Bang, and then put in the physics. So you put in things like gravity, you put in things like gas forms stars, and the gas follows the gravity and things like that into your simulation, and you see how the galaxies evolve. And then you can tune the simulation based on observation. So for example, we know how many galaxies of what masses there are in the local universe. We can measure that. And so you can say to your simulation, you need to end up, the end must have a distribution of masses that is similar to what we observe in the local universe. So here's that simulation. So what we're going to do is start off near the Big Bang. We're looking at the dark matter at the moment. So you can see it's kind of stringy. And as time is going by, those strings are starting to clump together more. So they're getting denser. You can start to see the blue patches get darker, and that's as the gravity is pulling them together. This component is the gas. So this is the fuel for the stars, and we've just zoomed into a single galaxy. And so you can see that as time is going on, we're about 10 billion years ago now, all this gas is starting to merge together, and it's probably there's a galaxy merger happening at some point, and then after that galaxy merger it starts to smooth out. So now we look at the stars in that galaxy. So the dark blue is the stars, this yellow is the gas, and you can see the stars make a much more smooth picture than the gas does. And so we're seeing how this galaxy is evolving through time, and we could compare this with observations we have of the real universe. And in fact, that's what people like me do an awful lot. And I consider it, you know, part of my job really is to observe the universe and try and find things that agree or disagree with simulations like this. And if we can break a simulation, if we can show that it's wrong in a specific way, that's how we learn, because that's how we learn that the physics that we put in was not quite right. And so we need to do something different in the physics. And then you can run the simulation again with slightly different physics and see how that changes what the evolution of the universe does and what the evolution of the galaxies do. So that's all I have to say for today. I'm really happy to take questions. Thank you for listening. It's great to see so many people.
Thank you so much, Julie. It was really a brilliant presentation. I want to say there were two things that I really liked personally. Well, the first thing was the simulation for the dark matter and how it can be connected to the galaxy and so on. And the second thing was when you say, do try this experiment at home, because I don't think that many people, when they're doing an experiment, most of them are telling you, do not try that at home. We've done that here. We are professionals. We took all the safety precautions and so on. But that experiment that you just showed is like, okay, go for it, try it. Since one of my favorite things was dark matter, I would like to ask you. We know that the dark matter exists in the galaxies, but in their halo and so on. But what's going on in between the galaxies? What do we know about the dark matter in between the galaxies?
Yeah, it's a great question. Different parts of the universe have different things going on between the galaxies. If we can show this slide again, I think that we've landed on a useful one by luck. So this is the end of that simulation video in this slide. And you can see here that the dark matter is shown as shades of blue. So the really dark regions here, that's where there's a lot of dark matter, and the kind of scattery, stringy bits, that's where there's not so much dark matter. And so at the center of all these very, very dark patches, there's probably a galaxy. And if we turned on the gas as well, you'd be able to see that. But you can see, in fact, that there's a lot connecting those regions. That's what we call filaments, and filaments of dark matter. They're very hard to observe because dark matter, by its very nature, is dark. It's kind of in the name. And we study the universe with light, which is the opposite of dark. So things get challenging, but we can measure the dark matter in a couple different ways. So one thing we can do is look at something like a galaxy cluster. And in a galaxy cluster, you see the effect of what's called gravitational lensing. And that's where light from a galaxy that is behind the cluster is distorted by the mass of the cluster. So the light bends through the mass in the same way that light bends through a lens. And we can see that, for example, in this image of the galaxy cluster, you might notice near the edges there's a couple of kind of curvy streaks, and that's actually gravitational lensing, bending the light from background galaxies. And we can use the positions and the shapes of those arcs to measure how much mass is in this cluster. And we can do that around individual galaxies as well as around the cluster. And so we can start to measure the dark matter from individual galaxies in the same way. What we've not done yet, well, no, that's not true. And then the other thing we can do is, rather than looking for these really extended streaks, we can measure statistically the shapes of galaxies. So on average, an elliptical galaxy will have a certain shape. And if we can measure statistically that in some patch of the sky, most of the galaxies are more squashed than that, and they're squashed in a particular direction, all in the same direction, then we can infer that there's dark matter in the way there that is causing that light to travel in a not straight line, which means that the images of those galaxies squashed in a coherent way. And that's something called weak gravitational lensing. And so there's people that are doing that to measure the dark matter as far away from clusters as they can. Now, we haven't done it in completely blank space yet because it's just a very, very hard measurement to do. You need really, really precise measurements, and there's a lot of challenges with doing that. But we're working on it. And the fact that basically every simulation we run shows that there is these filaments of dark matter between structures suggests that that's what's happening in the real universe, because we can't get the simulations to reproduce the real universe unless they have that structure going on. So there is probably dark matter between the galaxies, but it's very, very hard to measure it directly.
Brilliant. Well, thank you so much. Also, we do know, another question that we have is that we do know that there is a massive black hole in our galaxy. But do all galaxies have, in the middle of our galaxy, but do all galaxies have a massive black hole in the middle?
Yeah, they do. So every galaxy has a supermassive black hole, but not all of them is the supermassive black hole turned on. By turned on, meaning that it's actively accreting. So it's actively got new material falling in, which when that new material falls in, that makes it visible to us. It lights it up really bright. That's why there was a lot of X-rays from the center of that galaxy that I showed you in all the different wavelengths, is because there's a lot of black hole activity in the center of that galaxy. It turns out even more than every galaxy has a black hole. Every galaxy has a black hole whose mass is proportional to the mass of the galaxy. So there's something going on that said, if your galaxy is really, really big, then it's going to have a really, really big black hole. If your galaxy is really small, then it's going to have quite a small black hole. So there's something that is controlling the growth of the black hole and the galaxy at the same time in order to cause that correlation. So that's quite an interesting question, is how is that controlled and how is that stabilized? But yeah, every galaxy's got a black hole in the middle, but we can't measure so much from some of them because they're not actively accreting at very high rates.
Brilliant. Another good question is, well, someone asked, what is beyond Big Bang?
That is a good question. It's also a very hard question. The very short version is we don't really know. Our physics basically breaks down at the Big Bang. So our equations will take us as far as 10 to the minus 34 seconds before the Big Bang. I think that's right. So that's 0.000, 34 zeros, 34 zeros and then a 1 second after the Big Bang. We can get that far, but then who knows? Physics as we know it breaks down. So basically our equations don't work anymore. So you could make up a lot of different things. There's a lot of different options. There's a lot of people that have discussed this and thought about it. Really, there was nothing, because there was no time before the Big Bang and there was no space before the Big Bang. It kind of means there was nothing before the Big Bang, but it's really hard to think about absolutely nothing. Our brains can't comprehend it. So it's a challenge. I don't know.
I see. You said that theoretically in theory, basically our equations break when we go before the 0.34 zeros and 1 seconds before before that point, right? But how far back can we see?
I mean, I'm going to round up. So the Big Bang was 13.7 billion years ago. And we can see, we've got examples of galaxies that we think are a few 100 million years before that. So 13.4, 13.5, but we're kind of pushing that all the time. And it's a case of technology. So bigger and better telescopes can get us closer to the Big Bang, and seeing galaxies that are that far away. If we say, okay, I'm not worried about galaxies, I just want to study the universe as a whole, we can study something called the cosmic microwave background. and that's even closer to the Big Bang, and that was emitted at the moment that the universe cooled down enough that atoms reformed, and that means that light could travel, because when the universe was very, very hot, light couldn't travel through it because there was all this stuff in the way. The light would just bounce around inside, and so we couldn't see it. But the cosmic microwave background was emitted at that moment, and we've measured that, and that's one of the ways that we can measure things like how much dark matter and how much dark energy is there in the universe, is by studying the patterns in the cosmic microwave background. And so that's really close to the Big Bang. We will never be able to get closer than that because the universe is not see-through after that. So we can't see through it. So we can't see anything that's closer to the Big Bang than that.
And staying on the distance area, what is the nearest galaxy to our own galaxy?
The nearest big galaxy, and you'll notice I've been saying this big galaxy, is Andromeda, which is M31. That's one of the big spirals that I showed you at the beginning. But there's also a lot of what we call dwarf galaxies around the Milky Way and around Andromeda. And these are much closer. And actually, there's even more than that, in that not so long ago, there was dwarf galaxies that were near to the Milky Way that have since been gravitationally disturbed by the Milky Way, and their stars have been stretched out and joined into the Milky Way. So they're not necessarily individual galaxies anymore, but their stars exist within our Milky Way because our Milky Way destroyed them because of its gravity. It was the bigger one in that fight, and so it won. So yeah, there's a lot of dwarf galaxies quite close to the Milky Way, and in what you might consider the outskirts of the Milky Way, and then there's others that are in the process of kind of merging with the Milky Way. So I don't know whether you count those as separate galaxies or not.
Brilliant. I was also really fascinated, and I am really fascinated about the Hubble Extreme Deep Field. The whole concept of the whole thing, because basically you're pointing a telescope to nothingness, and in a couple of months you're getting thousands of galaxies, which is a bit mind-blowing. I would like to ask you if you know whether there are plans on doing something similar with the James Webb telescope, if hopefully will get launched in the end of October or in October.
Yeah, there absolutely is. So we point these telescopes at the blank patches of sky. They're carefully selected blank patches of sky. So for example, we study the same patches over and over with different telescopes because that gets us this multi-wavelength data. So we can study them in the radio and in the optical and in the infrared and in the X-rays and so on. And so James Webb will point at these same patches of sky, and it will do long exposures on these same patches of sky. However, its field of view, so how much of the sky it can see at one time, is quite small. I mean, Hubble's is already fairly small. James Webb's is even smaller. And so you probably won't get the same wide field coverage. You might get a tiny patch of it, but you're still pointing at a really dark bit of sky. And we can still compare that with what we would see with other telescopes and at other wavelengths. And we'll learn a lot about what's going on in those galaxies. We'll probably detect new galaxies that we didn't know were there because James Webb will be able to see fainter things than we can currently study. And we'll also get a different view on the galaxies that we do know are there now. We might not be able to get them very clearly at the moment. James Webb will be able to resolve them, so we'll be able to see finer details. And we'll be observing at a slightly different wavelength, so it will tell us something different about the stars that are in those galaxies because of looking at different wavelengths.
And a follow-up on that, why are you personally excited about James Webb Telescope?
I mean, I think there's two answers to that. One is it's an absolutely amazing piece of engineering, and it will bring us science that we have no idea about. So it's gonna do science that we can't really fathom today. And that this happens with every new piece of instrumentation, is that you see a hint of something and you follow it up with your new instrument, and you learn something brand new that you wouldn't have thought of before. And James Webb will do that in a huge variety of fields. So it's probably going to change. It will probably find new galaxies closer to the Big Bang than we've already found. It will be able to confirm some galaxies that we think are really close to the Big Bang, but James Webb will be able to tell us definitively whether that's correct. And it will probably look at things like exoplanets, so planets around other stars, and learn new things there. It'll look at things like star formation in our Milky Way, and we'll learn new things there. So in absolutely every field of astronomy, we'll be learning new things from this fantastic piece of engineering. For my research, it's going to be really cool because I look at these infrared galaxies, these ones that are really, really bright in the infrared, but they're very, very faint at optical wavelengths. So our giant space eyes would have a real struggle to see them. And James Webb will be able to do that in much more detail and much more sensitivity than we've done before. So we'll be able to see really what's going on in those galaxies in a way that we can't with the data that we've got. So if you remember the images that I showed of some of those galaxies where we had the red showing the infrared data and the green and blue showing the existing stars, by comparing that, if we looked at these with James Webb, instead of the blue and the green being these kind of fuzzy smudges, we'd probably get much clearer images. So we'll be able to see the structure in the blue and the green in much more detail. Some of these, there's not much blue or green there at all. We'll be able to see things that are much fainter than we can currently detect. So we'll really have a much better picture of what's happening in these galaxies. It will also allow us to measure some of the elements in these galaxies that we can't do at the moment because they're blocked by the atmosphere. So the atmosphere stops things like the lines of oxygen and hydrogen from these galaxies being visible to us. But because James Webb will be in orbit, it will be above the atmosphere. So we'll be able to study those as well. So we'll be able to see, where is the hydrogen gas in these galaxies, for example. And that's going to give us more of the physics of what's going on.
Perfect. And as our time unfortunately runs out, I would like to ask you a final question that apparently has been asked quite a lot during those sessions. Do you have any advice for basic telescope for a beginner amateur astronomer to look at the night sky for stargazing?
That's a really tough question. I think there's an awful lot you can do just by going outside to somewhere dark. And the key there is somewhere dark, and you need to let your eyes adapt. So without any equipment, if you go to a field that doesn't have any bright lights near it, if you can get away from a city centre or a town centre, that's even better. And sit there for at least 15-20 minutes and then look up. You'll be able to see an awful lot more than you could previously because your eyes adjust. Don't be looking at your phone screen. Don't be turning any torches on in that 15-20 minutes. You need to let your eyes fully adjust to the darkness. So that's the cheapest way. Obviously, getting somewhere that's properly dark it can be hard depending where you're based, but that's where I would start. You can do an awful lot with a decent pair of binoculars as well without going for a telescope. So if you get some binoculars, the trick then is to make sure they're steady. So finding things is hard, and then making sure you're not wobbling around is hard. But doing things like leaning on a fence post can make a big difference with that. And the same thing applies. Go somewhere dark to do it if you can. If you're looking at something like the moon, it will ruin your dark adapted eyes because it can be so bright. So just be a bit careful with that. And then for telescopes, there's a massive variety, and it really depends how much you want to spend. I suspect some of the cheapest end ones that you could get in a local high street store is probably not going to be that great, but I've not tried any of them, so I can't be certain that that's true. But yeah, I would start by just going someplace dark with just your eyes. If you've got some binoculars, take them with you and see what you can see with the binoculars, and then go from there. I'm afraid I don't have any more specific advice than that. So,
as your lovely feedback rolls in, I must say a big thank you to our moderators, Diego and Josh, and of course, a big thank you again to Dr. Julie Wardlow for giving up time in her schedule to come here and tell us those exciting things about galaxies and answer our questions.
Thank you for watching, and I hope you enjoyed learning a little more about our amazing universe. Our team from Lancaster University also runs shows for schools, community groups and more, both in person with our portable inflatable planetarium and online. But any in-person events are subject to current COVID restrictions. If you're a teacher, community group leader or part of a similar educational organisation, please do get in touch. We're particularly keen to make connections with those in our region of Lancashire and Cumbria, but we'd love to hear from you wherever you are. But for now, take care and keep learning more about the amazing wonders of our night sky. Thank you.